let's go one more here. Let's do one more example. Example number 3. Okay, let F be a map from R to R2. In other words, a curve in 2 space defined by f of t is equal to t and t squared. So this is the x-coordinate, right? This is the y-coordinate. It's a curve in 2 space. This happens to be the parameterization of the parabola in the plane. Okay, now let's go ahead and recover a function. Let me see here. Do recover a, you know what? No, not this is, well, that's okay. We've already started it. Let's go ahead and finish it. So recover a function y in terms of x. So now I've given you this parameterization, and we want to be able to recover some function the way we're used to seeing it. Y is a function of x. Dependent is some function of independent. Well, we're given the parameter t. The t is what's in common. So basically all you have to do is you have to eliminate the t from them and set y equal to some function of x. So x equals t and y equals t squared. Well, if x equals t, let's just go ahead and put this x wherever we see a t. So equals x squared. And there you go. That's it. So you can eliminate the t, the parameter, and you'll end up recovering some function y equals x squared. It becomes a lot more difficult. In fact, I'm not even sure it's, well, in 3 space and 4 space, but this is the power of parameterization. We've been dealing with simple functions all these years simply because we're accustomed to dealing in 2 space and 3 space. You know, our natural intuitive surroundings. We have a sense of paper. We have a sense of flat paper. We have a sense of 3-dimensional space. However, things could obviously become very much more complicated even when you're dealing in 3 space. 4 space, 5 space, 6 space, it becomes virtually impossible to deal with. So this is why we do parameterization. It is a much more sophisticated way of dealing with functions, and it happens to work for lower dimensional cases. In other words, you know, R2. So here's how you want to start thinking about functions. All right, so now let's go ahead and recap here. So what we've done as far as all these years, what you've been working with are maps, or general functions, y equals some function of x. Those are maps from R to R. In other words, you'll take some value x, you'll do something to it, and you'll spit out some other number, from numbers to numbers. Today we've introduced the notion of curves, which are maps from the real number line. You take a number and you create a vector to Rn. Well, we're also going to be going the other direction. We're going to end up talking about functions where what we'll do is we'll take a vector and we'll do something to that vector, and what we'll spit out is a number. And to top it all off, we're eventually, the most general is Rn to Rp. We're going to take a vector in n space, we're going to do something to it, and we're going to end up in spitting out a vector in p space. So we're going to work from one certain dimensional space to another completely dimensional space. And this is the power of multivariable calculus, that you can actually do this, that you can actually do the calculus that you know. Everything that you learned in single variable calculus still applies, and yet now it's going to become a little bit more sophisticated, more powerful, and it's really quite extraordinary. So next lesson, we're going to start with the actual calculus in n space. Till then, thank you for joining us here at Educator.com. Take care. Bye-bye.